In this lesson, we go through an old exam question about electrolytic cells. At this point, you should pause the movie and try to answer the question yourself before resuming. You can find the question as well as the table of standard reduction potentials from the link below. And while you're at it, why don't you like and subscribe? You can also visit my website for more resources. This question is about a copper chloride cell, and we know that it is an electrolytic cell. How do we know that? Because we have a power source. So we know that the energy conversion happening here is electrical to chemical. We have electrical energy driving a non-spontaneous chemical reaction. To remind yourself about how the copper chloride electrolytic cell works, click on that link over there. Now we know that this power source has to be a direct current power source, DC, not AC. Why? Because this DC current source would cause the two electrodes to become oppositely charged and keep that charge. So one electrode would become positively charged and stay positively charged, and the other negatively charged. Why is that important? Because the positively charged electrode will attract negative ions, anions. And once they get there, they will be forced to react. In other words, electrical energy will be converted to chemical energy. And at the negative electrode, the same kind of thing will happen. Positive charges, positive ions, cations, will be attracted. And once they reach there, they will be forced to react. When we discuss redox reactions, as happen in electrolytic cells, we make use of the table of standard reduction potentials for half reactions to help us. Now you need to make sure that you are using the same table that I'm using, otherwise everything will be back to front. From the South African data sheets, I'm using table 4B. This has reducing agents on the right, with the strongest reducing agents highest up, and oxidizing agents on the left, with the strongest oxidizing agents lower down. We need to understand what chemicals are present as reactants and then apply them to this table and understand what their position is telling us about what's going to happen here. The first trap that you might fall into is thinking that you have CuCl2 gas. Click that link there to remind you about the difference between ions and the elemental forms of substances. So here we do not have Cl2, elemental diatomic chlorine. Neither do we have copper, the metal. Instead, we have copper ions, which are hydrated. This is a concentrated solution, but a solution nevertheless. And that aqueous means that the copper ions are surrounded by water. And we have chloride ions, Cl-. And that too there simply means that the ratio between them is double as many of those as those. That's what that too means as well. So those are the reactants. Notice as well, don't fall into the trap of thinking that platinum in the electrodes is going to be part of the redox reaction. Platinum is inert, and it's used here simply to transfer the electrical energy from the battery to the solution to act as electrodes that do not participate in the reaction. So we go to our table of standard reduction potentials and we look for the positions of these two clear reactants. There is actually another reactant here, but let's get to that later. But these are obvious potential reactants. And so we take a look at where they are on this table. Now, before we do that, here we are speaking about an electrolytic cell. An electrolytic cell is kind of like the opposite in some ways to a galvanic cell. And so those rules where we could read the reaction in a C formation, which apply to galvanic cells, do not apply to electrolytic cells. Instead, now a weak reducing agent is going to act as the reducing agent. And so a weak reducing agent is going to be oxidized, and a weak oxidizing agent is going to be reduced. Why? Because the battery is going to force them to act against their natural behavior. In other words, electrical energy is going to be converted to chemical energy. Fitting with that, we find chloride ions quite low down on the right. They are weak reducing agents. They are going to be the reducing agent. So the chloride is going to be oxidized to chlorine through the loss of 2 electrons per 2 chloride ions. We find copper 2 plus ions here on the left, meaning that they're going to act as oxidizing agents here, even though they're weak oxidizing agents. You'll notice that copper 2 plus exists in 2 places, and there's also a Cu1 plus. Make sure that you choose the one which is copper 2 plus becoming Cu, the metal. And that is reduction because it's the gain of electrons. We look at our question and we see that at electrode A reddish-brown precipitate forms. We know that copper metal is reddish-brown in color. That tells us that this half reaction, the reduction half reaction, is happening at electrode A. From that, we deduce that this is the cathode because the cathode is the electrode where reduction happens in any kind of cell, electrolytic or galvanic. So what's happening at this electrode here is these copper ions are being reduced to copper the metal, which precipitates on the electrode. And that tells us that this is the cathode. It also tells us that this must be the negative electrode because it has to be negative to attract the copper 2 plus cations, which are then reduced at the cathode. And so that also tells us that this one here must be the opposite. It must be the positive anode. And we know that there we are getting oxidation. Those chloride ions are being oxidized to chlorine, which forms bubbles over here, CuCl2 gas. We're asked to give the half reaction that happens at this electrode. And there we have it. Cu2 plus, aqueous, plus 2 electrons gives us copper solid. Next, we're told that this copper chloride solution is replaced with a sodium chloride solution. So now we no longer have copper ions there. So we can't get copper precipitating there anymore. So how is this going to be different? How's it going to be similar to the previous situation? And how's it going to be different? Let's start with the similarity. Well, this is still going to be the positive electrode, and there are still chloride ions because sodium chloride, just like copper chloride, has chloride ions. And so you are still going to get this oxidation half reaction happening over there. But obviously, this reduction half reaction that happened before can no longer happen. You can fall into a trap easily of thinking that sodium ions are going to be reduced over there. True, they will be attracted because these are positive ions, and here we have a negative electrode. And so they would be attracted, yes, but they will definitely not react there. Why not? To understand that, let's go back to our table of standard reduction potentials, and let's speak about the distance between the oxidation and the reduction half reaction and what that means. It's important to realize that the closer together those two half reactions are to one another, the less energy is involved in the process. Or put another way, the further they are from one another, the more energy is involved in the process. Now, in an electrolytic cell, remember that we are putting in energy from battery to drive a chemical reaction. So the further the two half reactions are from one another, the more electrical energy that battery needs to put in, because it's more difficult to drive that chemical reaction because more energy is needed. And so the less likely that reaction will happen. The further they are apart, the less likely that combination of reduction and oxidation half reactions will occur for an electrolytic cell. Different for a galvanic, because remember there, you actually want them to be far apart, or rather they want to be far apart, because the further the two half reactions are from one another, the more energy is released. But we are speaking electrolytic now, so the further they are from one another, the less likely that reaction is going to happen. Why is that relevant? Let's take a look at sodium ions in this table, and you find them way up here on the top left, changing into sodium the metal, which is way up on the top right. That makes sense because sodium metal is a very strong reducing agent. It's an alkali metal. Alkali metals are very generous. They want to just get rid of that one valence electron that they have per atom. In other words, they're strong reducing agents. So sodium would love to be oxidized to sodium ions through the loss of an electron per atom. That they would love to do. And that happens very readily. Click there to see it. The opposite needs far too much energy to occur for this simple little battery when there is another alternative available. That ain't gonna happen. Another alternative available, what's that? Remember that these ions are hydrated. So it might seem as if the only reactants present here are sodium ions and chloride ions. But that's not really true, because there are also water molecules surrounding each of those kind of ions, and that water molecule can also react. Let's take a look at the position of those water molecules in this table. And sure enough, we find them closer to chlorine than sodium ions are here on the left. So, of course, this reduction half reaction can't happen. Instead, water gains electrons and so is reduced to hydrogen gas and hydroxide ions. So that is what's happening here at the cathode now. Next, the question tells us that in this electrolytic cell, we get bubbles at the cathode, at electrode A, and we must identify what those bubbles are. Don't fall into the trap of thinking that it's chlorine. We know that in the copper chloride cell, we get chlorine gas, so we might think, chlorine. Well, there will be chlorine, but that will be at the anode, just as we had it in the copper chloride cell. We can't have chlorine forming at both the anode and the cathode. The chloride ions would anyway not be attracted to the negative cathode. Negative and negative repel, they don't attract. So then what gas is it? Remember, the water is being reduced at the cathode. And what is it being reduced to? A gas, hydrogen. So we get hydrogen bubbles in that cell. Last, we're asked to explain why it's this reduction half reaction that will happen rather than that one. Now, I've been explaining that, but we need a very nice, quick, easy way to write this down. So whenever we ask a question like this, we must look at the two competing potential half reactions, and in both cases, they refer to reduction. And so we must refer to oxidizing strength. Because remember, the oxidizing agent is reduced. So these two potential half reactions are reduction, and therefore the two potential reactants are potential oxidizing agents. And the stronger one will be the oxidizing agent. So we see water is lower down here on the left, meaning that it is a stronger oxidizing agent than the sodium ion. So you will answer by saying water, H2O, is a stronger oxidizing agent than Na+. Be careful, not than Na, than Na+, the sodium ion. And therefore, in this reaction, water will serve as the oxidizing agent. It will be reduced rather than Na+ being reduced. I just want to point something out that might be confusing in terms of that. Remember right in the beginning I said that unlike in a galvanic cell, we get a weak reducing agent being the reducing agent and a weak oxidizing agent being the oxidizing agent. And now it might seem like maybe I'm saying something opposite. No, notice, whether it would be water or whether it would be sodium ions, that would be reduced. In either case, they would be weak oxidizing agents. In other words, you would read the reaction in the backward C. But when there's a choice between two possible oxidizing agents, then even in an electrolytic cell, the stronger one will be the oxidizing agent. If you enjoyed this movie, don't forget to like and subscribe if you haven't done so already. Leave me comments. What do you need me to cover in future movies? And please visit my website. There you can find many resources very easily, and you can quickly see what is going to help you at a particular time.